By the way, the same here. If you take a point in the interior, you can go in any direction, right? But if you are on the boundary, in the boundary you can also go in all directions. But when I say all directions, I mean to go in some directions and stay within the domain. If you want to stay within the domain, you can go inside, you can go along the boundary, but you're prohibited from going outside. So some directions are prohibited. That's what it means to be on the boundary. Likewise, if you look at the circle at the base of this dome, you see that you cannot go down. This is prohibited. You can only go sort of up on the dome, or you can go along the boundary, right? That's the difference between this point. Even if you have a point even very close to the boundary, you can still go down a little bit. So that's the difference. Any other questions? Yes. Right. Not every, because see, I have not put the integrand yet. We'll have to learn that. See, the trick is that at the level of domains, you take a boundary. But at the level of the integrand, you take the derivative this way. So in other words, what you will have here, will schematically write it as a derivative of something, which is on the right-hand side. So it's not the most general integral you see here. It's the integral of something which is the derivative of something from the right. So this is not a formula which allows you to express a double integral as a single integral, but only allows you to express a double integral of something which is a derivative as a single integral of the quantity of which it is a derivative. That's the idea. But we'll talk about this more later, so I don't want to spend too much time making it precise at the moment. Okay. So what we need to do now is to describe the kind of objects that we'll have to integrate to really do justice to this kind of formula. And the point is that it's not enough to just integrate functions. We have to integrate more general objects, which are called vector fields. And of course, everybody knows what this concept is, maybe not the term. So it's actually a very intuitive concept, which I'm going to explain. So the way to think about it is as follows. First of all, let's remember what is a vector to begin with. What is a vector? A vector, we could work on everything that I will say will be can be applied in R2 and R3 on the plane and in space. But it will be easier to say in R2 because there's fewer components and so on. So let me say first in R2, and then we'll generalize into R3. R2 on the plane. What is a vector in R2? A vector in R2, as we know, can be, well, first of all, we can draw it like this. Right? It's an object which has not only a magnitude but also direction. So this is a vector. Right? But algebraically, we represent it by a pair of numbers. We write it as PQ, say. So it's not just a single number. It can be represented by a pair of numbers once you choose a coordinate system, PQ, and we also use a different notation, PI plus QJ. Remember, we've learned this was IJ was our notation for the unit vectors along the x axis and along the y axis. Okay. So that's a single vector. This is just one vector. But suppose you would like to attach a vector to each point on the plane. Suppose we have attached a vector, a quantity like this, to each point on the plane. So what is this going to look like? Well, say this point will have this vector, and then this point will have that vector, and then this point will have this vector, and this point will have this vector. You know. So a priori, they can all be different. They can all be different. There should be no connection. Of course, the simplest situation would be just assigning the same one to all points, but it's kind of boring. So you can actually just assign them in a very complicated way. So this actually occurs in practice, in reality, in different ways. And the simplest way to think about it is as wind maps. Wind maps. Actually, it's funny because in the book, the picture which illustrates vector fields is the picture of a wind map of a San Francisco Bay Area. So I guess for a good reason, because our winds are changed and they kind of have an interesting pattern. Some years ago, I used to do a lot of windsurfing, and I remember there was this website where you could go and you get a beautiful picture of the winds, real time. The winds real time all across the San Francisco Bay. So if you want to windsurf, so let's say that this is a bay, roughly. This is San Francisco. This is a Golden Gate Bridge. This is San Francisco. So it's very schematic, okay. And this is Berkeley. I'm looking from the top. Oh yeah, it's important to say that, right? I'm looking from the air. So let's say there are many spots across the bay for windsurfing. So let's say here in the Berkeley Marina, there's Emeryville, and here you have a Treasure Island, and so on. And so if you look at this map, you know right away that the wind here is, say, east points in the eastward winds, and then like here will be north, and here will be south, whatever. Right? So that's the meaning of, you've all seen such maps. You can imagine such maps. Because the thing about wind is that the wind does not just have magnitude, the force of the wind, but also has direction. It could point in the northern direction, the east, the west, south, and so on. Right? So wind at a given point is a vector. It's not a number, it's a vector. But wind is everywhere, so therefore, at each point you have a vector, the wind vector. Right? So wind represents a vector field. So this is a vector field. So a vector field is an assignment of a vector to each point on the plane. Or maybe some given domain on the plane. Maybe not everywhere, but I mean, of course, say here I talk about a particular domain, which is on the map, say, which is just San Francisco Bay Area. I'm not talking about the entire United States or the entire state of California. So this is a vector field. Is this clear? Okay, so now let me contrast that to a function. Up to now we've talked about functions, and we've been integrating functions. A function would be just, a function means assigning to each point, not a vector, but a number. For example, think of a barometric pressure. At each point you have a barometric pressure. Barometric pressure is not a vector, it's a number. So at each point you have a barometric pressure, at each point you have a number, so you get a function. What we normally call the function is assignment of a number to each point on the plane. And vector field is almost like this. The only difference is that we assign to each point not a number, but a vector. But in some sense, why not, right? Okay, so how would we represent such a vector field algebraically? Algebraically, well, each of those vectors would have two components. But now these components depend on the point. So a point xy, so if you have a point xy on the plane, would have a vector which will have components p of xy and q of xy. So we will write p of xy, q of xy, and we will put the square brackets as we usually do, right? Or we can also write it as p of xy times I plus q of xy times j, just like we did before. just like we did before, pq or pi plus qj. The only difference is that now p and q themselves become functions. Right? So it's p of xy, q of xy. And we will call this vector field f of xy. So oftentimes, for practical purposes, you can say that the vector field is nothing but a pair of functions. So it's not a single function, it's two functions, because the vector has two components, and now each component becomes a function of xy. But really reducing it to a pair of functions is not a good idea, because it kind of strips the vector of its geometric meaning, because the vector is much more than just a pair of numbers. First of all, this pair of numbers can be given only once we choose a coordinate system, right? I mean, after all, what are these numbers, p and q? I have drawn them here. Those numbers are the projections of the vector onto the x and y axis, right? But if I choose a different coordinate system, the vector will stay the same. The vector will stay the same, but the projections will be different. So you have to remember this algebraic representation really depends on the choice of coordinates, right? But the vector itself doesn't. In other words, let's say here is a map of San Francisco Bay Area. San Francisco Bay Area doesn't know anything about coordinates. It exists without any coordinates. Somebody will come and make a coordinate system like this, but somebody else will come and make it like this. Who knows? Maybe for some purposes this will be more convenient. Okay? The wind doesn't know about the coordinate system. This vector will stay. The wind will blow in this direction no matter what coordinate system you prescribe, right? So the wind is for real. It's a real geometric object, and the two numbers that we assign, or two numbers which we use to represent this vector, is an abstraction. Is a way to represent them algebraically, but this way of representing it algebraically depends on the choice of coordinates. So that's why I'm saying that reducing a vector to a pair of numbers, or reducing a vector field to a pair of functions, somehow doesn't do justice to the object. It strips it of its geometric meaning. Nevertheless, in our calculations, oftentimes, we will be working with vector fields as though they were just represented by these two functions. So for all practical purposes, we just have to integrate those functions, say, or differentiate those functions independently. Okay? Yes? That's right. So let's say at this point, this is point xy. So you have this vector. So here's another point, which we'll have, say, x1 and y1. Coordinates. And at this point, let me use a different chalk to represent vectors. So let's say this vector goes like this. This is a vector assigned to the point xy. To the point xy. And say the vector assigned to this point will be this vector. So this vector will be p of x1, y1, comma, q of x1, y1. Right? A priori has nothing to do with it. You see what I mean? At each point you have a vector. What? Well, a function represents a bunch of numbers, right? So in other words, say this function, what is a function? Function is a number attached to each point xy. For any xy, you have some number. And now you have these two functions assembled into a vector, right? So you have a vector for each xy. The vector attached to xy, say, would be this vector, and the vector attached to x1, y1 will be this vector. The vector attached to x2, y2 will be this vector, and so on. It's represented by a formula. So let's look at an example of a vector field. Okay, so the simplest example would be, let's say that f of xy is just I. What does it mean? It means that p in this case is 1, and q is 0. Right? From the point of view of this general formula, p times I plus q times j, p is 1 and q is 0. So I just write it as I. What is the geometric meaning of this formula? Well, it says that the vector attached to any point is one and the same vector I. Right? So what does it look like? Well, at each point I just have vector I. This is vector I. This is a vector which is parallel to the x-axis and has magnitude 1. So here I have this vector, and here I have this vector, here I have this vector, and so on. I cannot draw them all, because I cannot account for all the points on this blackboard, or even like on small parts of the blackboard, because I have too many of them. So I'm just drawing a few of this. And this is what's called the diagram, the vector field diagram. And that's what is meant to, it's not meant to represent the entire vector field, because of course, inevitably, no matter how many vectors I will draw, I will miss some points. There are infinitely many of those. This is just meant to give you an idea as to what the vector field looks like. Because, of course, the point is that in these studies, in this course, we are going to consider kind of nice, the vector field will consider will be nice. In the sense that the vector field, in general, the vectors will change from point to point, but they will change in a continuous manner, in a smooth manner. So even if you know what the vectors look like at sort of a certain number of points, this should give you an idea as to what vectors look like in between. Okay? So this is a simple vector field. It's called a constant vector field. Okay, so let's do something more complicated. Something more complicated. Question? Yes, shoot. That's right. Nor if we say vector field on the plane. That's right. Very good question. So the question is, do we have to assign a vector to every point on the plane or not? Okay. And it's the same kind of question is as asking, suppose you have a function. Does it mean that we have assigned a number to each point? And the answer is it depends. Right? By default, if I just say this is a function on the line or on the plane, I'm saying that it is defined everywhere. But we know that there are many interesting functions which are not defined everywhere. For example, even in a one-dimensional context, say function f of x equals 1 over x. This is an important function, and it's not defined as 0. So this function assigns a number to every point x on the line, except x equals 0. Sometimes we only want to know the values of the function on a certain domain, let's say in an interval from 0 to 1, and we don't care what happens at other points. Same goes for the vector fields. But if we say vector fields on the plane, we kind of implicitly saying that there is a vector attached to every point. But in many situations, first of all, a formula that we write will not be well defined at some points on the plane, right? So then it means that the vector field is not defined there. Or it could be that we just only care about the values across a certain domain. So we only define it on that domain, we don't care what happens outside. Any other questions? All right. So next example, let's say f of xy equals x times I. No, let me use the y. xi plus yj. Okay, so this is slightly more interesting. This is certainly not a constant vector field, because now the function p of xy is not a constant function, but it is function x, and q of xy is a function y, right? Let's see. So what does it look like? So for example, let's say we take the point 1, 0. If we take the point 1, 0, I should put an arrow, of course. When I talk about vectors, I have to put arrows on top. That's the usual notation. So let's say f at 1, 0. This is point 1, 0. If I substitute 1, 0, I get I. So here is going to be vector I, just like in the previous example. But this is really the only point where it is going to be vector I. Let's take, for example, the point 0, 1. 0, 1, we get j. So this is a point 0, 1, and we get this vector. And likewise, for example, you can take negative 1, say you can put plus minus 1 here, and this will be plus minus I. So this will go in this direction. This will be negative I at this point. And likewise, here plus minus 1 will be plus minus j. So this will be this vector. So this already kind of tells you what the pattern is. The pattern is that at each point, in fact, the vector is going to go in the direction of the position vector of that point. For example, this is point 1, 0. The position vector of this point is this vector. And the value of our vector field is going to be just that vector. You see? So, but we draw it. See, it wouldn't be right to draw this vector starting at this point because we are drawing this picture with understanding that the vector that starts at this point is the vector assigned at this point. Right? But of course, as we discussed many times, the same vector can be represented in many different ways. We can start with any point. Here we start with the point to which it is attached. This vector is attached to the point 1, 0, so we draw it here. This vector is attached to the point 0, 1, it's written here, so we draw it here, and so on. And more generally, if we have a point with coordinates x, y, the vector attached to this point is going to be xi plus yj. But that just happens to be, in this example, it just happens to be the position vector of this point, which we normally draw like this. So what should I draw then for this point? I have to take this vector and transport it here, so that the initial point is here and not here. Right? So then I end up with this one. I just transport it here. So that's the vector ij. This is vector xi plus yj, which is prescribed to this point. And it's the same as this vector. So I can now kind of draw more. So you see they all move away from the center. They all move away from the origin. At each point, the direction is exactly away from the origin. But the magnitude actually changes. The magnitude changes. The magnitude is equal to the distance from the origin. So if I go far away, the magnitude will be even higher. If I'm very close, the magnitude is very small. Okay? So that's the vector field that I get. It's kind of it's an explosion. It's kind of an explosion. Right? Well, it's not quite an explosion because if you have an explosion, it actually decays as you go farther away. But here, actually, the force increases. The magnitude increases. It's like a universe expanding. That's right. Well, it's one of the scenarios. Of course, we would like to think that it's expanding, but it is expanding now. But we don't know what will happen eventually, and it might all collapse. But not before the end of the semester. Don't worry. So, unless some of those formulas are incorrect. So, okay, but let's suppose that you wanted the same kind of deal. In other words, you wanted the vector field which also goes away from the origin, but you didn't want the magnitude to be higher and higher, greater and greater. Let's say you wanted the vector field where each vector has magnitude 1. This is very easy to do. You can just convert each of those vectors into a unit vector pointing in the same direction. So let's say the third example would be you would have to take x times I plus y times j and divide by the magnitude. And the magnitude is x squared plus y squared. Square root of x squared plus y squared. So now each of these vectors is a unit vector pointing in the direction of the position vector like before. So in other words, the magnitude is not increasing, but it stays fixed, equal to 1. Or if you want the magnitude to the vector field to decay, you can divide by a higher power of this. So for instance, you can also take f of xy equals xi plus yj, but divide by, actually you can divide by the square of this, but it is a little better to divide by the cube, and I'll explain why. Squared plus y squared 3/2. If we do that, then the magnitude of this vector, or the length, if you will, of this vector, will be what? When we take the magnitude, we get square root of x squared plus y squared in the numerator, right? And we get is this right? No, actually, I don't want 3 over 2. I want actually, how do I want it? I want to have twice square of the length. That's right. No, it was correct. That's exactly what I want. So the magnitude would then be 1 divided by x squared plus y squared, right? Which is the square of the length, which is the square of xy. So that corresponds to the vector field where the magnitude is proportional to or equal to the inverse square of the length of the distance. And this is very typical for very important forces in nature. So this is going to be the behavior of this vector field is like the behavior of the force of gravity, or the electric force, electromagnetic force. Okay, the force of gravity is inverse proportional to the square of the distance, and that's exactly what we get. But because in the numerator we have the position vector itself, we divide by, instead of dividing by the second power, we divide by the third power. So that when we take the length, there will be 1 power here and 3 powers here. So only 2 powers will be left. Okay? Yes? Because I would like to get the vector field such that the length of a vector is equal to the 1 divided by the square of the length of this. Because this kind of behavior is characteristic of important forces in nature, like the force of gravity. You know that if you have two masses, say Sun and Earth, two masses, then two objects, and then the force of gravity is inverse proportional to the square of the distance between them, and also proportional to the masses. And there's some coefficient of proportionality. Do we do what? Do we cube every problem we do that? This is just one example. Okay, one example. I'm not saying that all vector fields look like this. It's just one vector field. Okay. All right. So